Good morning everyone. So, we are moving into the next separation process, that is chromatographic separation process. But before that, I would like to solve what I have discussed in the last class, that I would like to solve one problem on centrifugal separation process. It is a scaling up problem. Once we will solve this problem, we will move on to the next topic of our chromatographic separation process. So, let us first do a problem on scaling up of a centrifuge. Scaling up of a centrifuge. Now, in this problem, it is we are dealing with a slurry. Slurry means again solid plus liquid, and we would like to separate the solids from the liquid stream using the centrifugal forces. It contains the solid particles of density 1200 kg per meter cube. It has to be clarified by centrifugation. The solution density is given as 850 kg per meter cube. The solution viscosity is given as 80 Cp. Since the slurry contains huge amount of solid, its viscosity will be more, and let us say we have a centrifuge. Let us say centrifuge 1, okay, which have a bowl, tubular bowl with R2. These specifications are given. 0.02 meter and R1 is 0.01 meter, and height is given as 0.25 meter. Okay. And we are going to use operating condition of RPM as 15,000 revolution per minute, and flow rate we are going to have 0.002 meter cube per hour. Okay. So, using this centrifuge, now we would like to we would like to scale up this centrifuge. So, what we have to do now is that, suppose we are looking for a centrifuge which can handle 1.5 times flow rate, that is Q. In the new centrifuge, R1 and R2 remain same, and we have to find out the length of the centrifuge. Length of new centrifuge, assuming the revolution rotational speed is same in both the cases, both the centrifuges. Rotational speeds are same for both centrifuges. Okay. Now, let us look into the solution. If we remember that we are looking for a particular parameter which will be constant in both the cases. What is that parameter? That parameter is terminal velocity due to gravity. So, if we equate that then we will be getting Q1 by epsilon 1 is equal to Q2 by epsilon 2. This is the scaling equations that we have already talked about. So, Q1 by Q2 is nothing but epsilon 1 divided by epsilon 2. Now, if you remember the expression of epsilon, the sigma value, this sigma is basically, it talks about the geometry and characteristics of centrifuges only. It does not talk about the characteristic of the fluid and the solute system. So, therefore, if you look into the expression of sigma, it becomes omega square pi b R2 square minus R1 square divided by 2 g ln 2 R2 divided by R1 plus R2. So, if you remember in our problem statement, the R1 and R2 and omega are same for the two centrifuges that we are talking about, we are discussing, and only the parameter that will be varying is the length of the centrifuge. Therefore, Q1 divided by Q2 will be nothing but B1 divided by B2. All the other things being other terms remain constant, remain equal, they will cancel each other. So, therefore, Q1 by Q2 will be is equal to B1 by B2, and if you put the values of Q1 by Q2 is and what is Q2? Q2 is nothing but 1.5 times Q1. So, this becomes 1 by 1.5 is equal to B1 by B2. So, therefore, your B2 will be 1.5 times B1. So, given the value of B1 is 0.25 meter, so it becomes 0.375 meter B2. So, the length of the new centrifuge becomes 0.375 meter, and whereas the old centrifuge was 0.25 meter. So, if you select a centrifuge of the same dimensions of R1 and R2, but if you select a length of 0.375 meter, then it can handle a flow rate which is 1.5 times more than the flow rate that we are talking about, the flow rate of the earlier centrifuge. Now, this example gives an idea how to scale up various geometrical parameters of the centrifuge. For example, if you would like to keep the value of B constants, if you like to vary the R1 and R2, that gives an idea how to how different parameters will be geometrical variables will be determined when you are going for a scaling up operation. And so, this gives a complete idea of scaling up of a centrifuge. Okay. Next, we will move on to the next separation process, that is chromatographic separation process. Now, it is an extremely powerful tool for separation and analysis of complex mixture. This is a powerful tool for separation and analysis of a complex mixture. Okay. Typically, we are talking about the separation of organic materials. Okay. And it's an analytical high pressure liquid chromatography. I will just draw a schematic of it. First, you will be having a solvent tank. This is a solvent tank. From the tank, there is a pump which pumps the liquid into the column. So, you will have a column, and there you pump the solvent into the column, and somewhere in between, before entering into the column, you inject the feed. So, feed is injected. Okay. The effluent, the feed being mixed up with the solvent, it goes through the column, and the effluent will be coming out through a detector, and this detector is sometimes it is refractive index detector, or sometimes it is a UV visible spectrophotometer, and then it goes to there is a flow meter out there to detect the flow rate of the solvent. So, this is a typical schematic of a high pressure liquid chromatograph. Okay. Now, a typical chromatograph will contain certain features. So, let us note down those features. Salient features of a chromatogram of a chromatograph. So, first feature is, for liquid system you must be having a pump to push the liquid through the column. for liquid system, a pump is used to push the liquid through the column. Secondly, a pulse of feed is injected into the system So, we are not injecting the feed continuously, we are just injecting a pulse of feed is injected in the system. Thirdly, the column is often enclosed in an oven to maintain the temperature. Column is enclosed in an oven to control or maintain temperature. Lastly, you must be having a detector that analyzes some properties like refractive index, UV absorbance, etc. So, detectors are used to analyze properties like refractive index, UV absorbance, etc. And these properties, these values of this refractive index or UV absorbance values, etc., are connected to concentration. Okay. So, one can have the value of refractive one can have a pure solution and can get a calibration curve, and that those can be utilized in order to find out the concentration of the actual sample. Now, let us look into the purpose of the column. Suppose you will be having a feed mixture, that means a mixture contains different kinds of components. So, for a feed mixture, now it will be showing, suppose a mixture contains there are 4 or 5 components, then you will be getting 4 or 5 peaks corresponding to each component. So, the resolution will be depending upon how good your column is. So, if you look into the absorbance value and time of, if that is the residence time of each of the material that is going through the column, you will be getting various peaks. Okay. And the area under each peak will correspond to, let us say these 5 minute, these let us say in minute, this 10 minute. So, this peak corresponds to component A, this peak corresponds to component B, C, D. So, various components will be having various properties, and we will be looking into why these properties will basically the cause to have different residence time. So, at different residence time you will be getting peaks of corresponding component. Now, the area under this curve will give you the value of the concentration. Okay. Now, typical concentration of a feed. Now, let us look into the typical conditions of a chromatograph. The feed concentration will be extremely dilute. Feed concentration will be in the order of 1 ppm, that means no, it is less than that, 1 milligram per ml, right. It will be extremely small, and typical column dimension that we are talking about, that will be in the order of 10 centimeter into 4.6 millimeter. That means diameter 4.6 millimeter and length is around 10 centimeter, that is typically a column dimension. it contains a bed of materials which is nothing but the material of column. WCX is a typical material of column and the particle size will be in the order of 7 to 5 to 7 micron basically, and the pore size inside the materials will be 300 angstrom. It will be in that order of magnitude. The possible mobile phase composition can be anything. That means, we are talking about the solvent composition. Okay. I am just giving an example of mobile phase composition. A typical example of mobile phase composition is 0.05 molar phosphate with sodium chloride. You can have various other mobile phase composition as well for typically for different uses. Typical flow rate that you are talking about will be in the order of 1.5 ml per minute. So, I am giving this figure to identify that what will be the typical values of various operating condition in a chromatograph. The detection mode is UV region, ultraviolet region, okay. And for protein you have to detect. So, depending on the solute you are going to analyze, the wavelength of UV detection will be used. For protein absorption, for protein solution, the wavelength of UV or ultraviolet is set at 280 nanometer. Okay. So, that is a typical value, and how much the amount of feed that you are going to inject, the typical amount of feed that you are going to inject will be extremely small. It will be in the order of microliter. It will be around 8 microliter, 10 microliter. Amount of feed to be injected will be 10 microliter, and the peaks in the response, they correspond to various components, and the area under the curve to be compared with calibration curve of each pure component. That means, if you are having a mixture of 4 or 5 pure 5 components, then you have to take the pure component of each species, then inject 10 microliter of each pure species into the HPLC column. In that, when you are running a pure component, you are supposed to get only one peak. That peak will correspond to a pure component, and you have to use the same mobile phase composition of the mixture. That means, you are using same mobile phase composition for each and every pure component and area under the curve. So, after getting injecting each and every pure component, you are going to get a peak, single peak for each of them, if it is let us say 99% pure or 98% pure. Now, the area under, so for now what you can do, you can take various concentration of the pure component and inject them. So, that means, the area under the curve at a particular retention type where the peak will be appearing, that will be varying in area. So, therefore, this area under the curve will be basically a function of concentration of the component that we are talking about. So, now you take the concentration, you know the concentration and you know the area, and plot area versus concentration, that gives the calibration curve of a pure component. Similarly, suppose you are talking about 5 components in a mixture, you inject different concentrations of these 5 materials into the column and get the calibration curve of every each 5 components. Now, when you put the mixture using the same mobile phase composition, you put the mixture, you inject the mixture into the column and you will be getting, let us say, 5 peaks one after another, and the area under the curve will be you can means the software itself will give the area under the curve value. You can go to each and every calibration curve of corresponding to every component and can get the concentration values. That is how it will be working. Now, let us look into the working principles of. So, that is how one will calibrate and get the values of measure the concentration in a typical chromatography column. Okay. Now, let us look into the underlying principles of chromatographic operation or chromatographic separation process. Okay. Now, there are various systems. So, one can have gaseous system, one can have liquid system, one can have a various type of system. Let us talk about the gaseous system. In case of gaseous system, instead of a solvent or instead of a solvent mixture, you will be having a carrier gas. Okay. In case of gaseous mixture, instead of a mobile phase, as a solvent, the mobile phase was solvent in case of liquid, right. In this case, the mobile phase will be a gaseous, a carrier gas is used. Okay. Now, this carrier gas can be hydrogen or helium. Hydrogen or helium, and in column an adsorbent is used. And a typical adsorbents that we are talking about are zeolite, silica gel, activated alumina, etc. Okay. Let us look into the gas liquid chromatography, GLC. GLC is nothing but the gas liquid chromatography. In gas liquid chromatography, an inert porous solid is coated with a viscous high boiling liquid. The first feature is that an inert porous solid is coated with highly viscous high boiling point liquid. So, what is the purpose? The purpose is basically this phase, this liquid phase which is highly viscous, it is almost a stationary phase. That means, it does not move on the solid surface, it will stick to the solid surface. Number 1. Number 2 is, since it is having its boiling point is quite high, then you can go for a higher temperature operation as well. So, that it will not evaporate. So, therefore, this stationary phase will cause the separation. In a gas liquid chromatographic, this stationary phase, this liquid stationary phase that will be encompassing the solid particle causes the separation. Stationary phase causes the separation. Thirdly, the characteristic of the solid should be inert, okay, because the liquid, the stationary phase is basically the separation causing phase. So, solid has to be inert, otherwise it will be interfering into the mass transfer. It should be porous, it should be inexpensive. These are typical characteristic of the solid. Example of a solid is diatomaceous earth. It is basically a material, so that is highly porous and it is easily available. Okay. And solute in feed can dissolve in stationary phase. So, solute in feed, what it does, it gets dissolved in liquid phase and then vaporize in flowing gas. Okay. So, what is the separation? Separation is therefore is based on relative volatility and it is usually an adsorption stripping operation. Separation is based on relative volatility and it is essentially, it is mainly adsorption and stripping operation. So, therefore, you are adsorbing the solute is adsorbed in the stationary phase on the solid, and when you are passing the gas, the solute is dissolved or getting stripped off from the stationary phase and it is coming into the gaseous phase. Okay. Now, let us look into the disadvantages of GLC. Of gas liquid chromatograph. Number 1 is the stationary phase, although it has a high boiling point, it slowly evaporates. Okay. Slow evaporation of stationary phase occurs. Okay. So, what it does, it affects, it leads to two harmful effects. One is the column criteria is changed. Column criteria is changed because it has a capability. Initially, it was having a capability, but if it vaporizes to some extent, its capability decreases. So, column criteria is changed and it contaminates the product. If the stationary phase, if the liquid phase that is producing producing a film over the solid, if it evaporates, it acts as a contaminant to the gaseous stream, right, in the product stream. So, it goes into the product stream. So, it acts as a contaminant. Now, let us look into the capillary gas chromatography. It is a glass or fused silica capillary is used in this case. A glass or fused silica capillary is used with a coating of adsorbent or high boiling solvent on the wall is used. Okay. But since the stationary phase quantity amount is less, it has its capacity is limited. So, the disadvantage is, since amount of stationary phase is small, its capacity is limited. So, it has a limited capacity. On the other hand, open capillary, it has a little resistance to mass transfer, less resistance to mass transfer, and sharp separation is observed. Okay. So, that is capillary gas chromatography. Let us look into another chromatography, that is called liquid chromatographic or LLC. Now, the salient features of liquid chromatography are: number 1, a stationary liquid phase is coated over an inert porous surface. A stationary, it is just earlier, liquid phase is coated on an inert porous solid. Number 1, separation is essentially an extraction process. Okay. And it is useful for separating non-volatile solution. Highly efficient for separation of non-volatile solutes. Okay. Now, let us look into the difference between LLC and modern high pressure high performance liquid chromatography or HPLC. Differences between liquid chromatograph and high performance liquid chromatography. This high performance liquid chromatography, the other name in short it is known as HPLC. The first difference is the inert solid is silica in both the cases. Inert solid is silica, stationary liquid phase is chemically attached to the solid. So, this is basically column characteristic. So, these materials are inbuilt within the column. So, when you are purchasing the column, the whole column contains this solid as well as the embedded liquid along with it. Okay. So, you are not doing anything basically. So, you are basically passing the solute along with the solvent through the column. So, stationary liquid phase is chemically attached to the solid. So, therefore, there is no loss of stationary phase, no loss of stationary phase. Since it is chemically attached, the attachment is stronger than any physical attachment like adsorption. So, there is less probability of losing this stationary phase when the solvent will be going through it. So, most common stationary phase is C8 or C18 compounds attached to silica gel. That means, we are having a carbon component of having 8 carbon atoms or 18 carbon atoms. That is why those are attached to the silica gel, that is the inert porous solid. That is why these columns are often termed as C18 column, they are termed as C8 column. Okay. So, you must be ordering for a C8 column, okay, or you must be ordering a C18 column. That means, the C18 compounds will be in the liquid phase and they will be attached chemically, they will be bonded chemically over the silica gel particle. Okay. And typical solvent is water. The second criteria, second feature is that the short column have very small diameter. Short column and they have small diameter. Packings are operated at high velocity and pressure drop. So, since the column itself is very short and the packing are very close, so the operating pressure drop will be quite high in the high performance liquid chromatography. The typical conditions are the column is 10 to 25 centimeter long, 4 to 8 millimeter in diameter, internal diameter. Typical packing dimensions are 3 to 9 micron and delta P will be around 1000 psi. You see, since the packing materials are so small in diameter, they form a closed packed material within the column. So, therefore, in order to effect a flow, you must be having a very high pressure drop and the high pressure drop will be in the order of 1000 psi. Okay. But what is the advantage? The advantage is changing solvent has major effect on distribution coefficient, hence on separation. That means, if you change the solvent instead of water, if you use some other mobile phase, okay, for example, acetonitrile. Okay. So, change in solvent has major effect on distribution coefficient of solute and hence separation. Okay. So, you can suppose you are not getting with a particular solvent, you are not getting the required separation, or so that the peaks those are getting, they are almost superimposing. So, you can change the solvent, you can change the flow rate as well slightly, and then you can run the column and see whether these two peaks are different are coming one after another or not with a sufficient gap without overlapping. Okay. Next, we will just look into the GPC or size exclusion chromatography. This is often known as SEC. Now, in this case no adsorption takes place. Steric exclusion of the solute plays the most important role. What is steric exclusion? It is nothing but the size exclusion. That means, if the particle has larger size compared to the pores, it will be excluded, it will not go into the pores. Okay. Steric exclusion of solutes causes separation. So, this is useful. So, therefore, this method is extremely useful for separation of larger molecules from smaller molecules. The solid matrix is cross-linked polymer gels for example, agarose, cefadex, polydextran. This is often known as cefadex. So, these materials they are used for preparation of the solid matrix, or and these solid matrix are kept in the column, and the exclusion of the depending on the size, the larger particles will be separated from the smaller particles. Okay. The smaller particles are allowed to flow along the solvent through the column, the larger particles will be excluded. Okay. So, the principle of working principle is it's also known as the migration chromatography. Where solutes sorb and desorb and all solutes move at finite but different velocities. Okay. So, this is a general principle of any chromatographic column. Now, let us look into the solute movement system, solute movement through the column. Okay. This entirely depends on the packing structure and the nature of the packing. So, solute movement, the first factor, it depends on packing structure and nature of packing. Solid particles should be sorbents having high porosity. That means, solid particles, that is those are present into the column, they must be having high porosity. They should have large surface area per gram of the sorbent. This is a typical characteristic, large surface area per gram of sorbent, so that their adsorption capacity will be more. Okay. Now, particles must be porous. Why the particle must be porous? Because it will if the particles are porous, it will affect more separation, because some particle will be adsorbed on the outer surface as well as inner pores. So, there are lots of pores, those are going into the structure. So, solutes will be not only adsorbed on the outer surface, they will be going into the pores and they will be getting adsorbed there. The separation will be more, or it will be more efficient. Okay. So, let us have some definition of porosity of the particle. Epsilon p is the porosity within particle. Okay. Epsilon e is the average interparticle porosity. So, so that means this epsilon p is intraparticle porosity. That means this porosity corresponds to the porosity of the particle, and epsilon is average interparticle porosity. That means this porosity between the adjacent particles. So, this is interparticle porosity, and this is epsilon p is nothing but the intraparticle porosity. That means epsilon p corresponds to particle porosity and epsilon e corresponds to interparticle porosity. So, that is the porosity that exists between the adjacent particles. So, you can have the definition now. Epsilon e is basically volume between particles. This is epsilon e. Divided by total volume of the packed bed. Epsilon p is volume of fluid inside all particles. This is the particle porosity. Volume of fluid inside all particles divided by total volume of all particles. Okay. So, therefore, once you define these two quantities, you will be in a position to define the total bed porosity, epsilon t. Epsilon t is total bed porosity, and total bed porosity is defined as sum of voids within particles and between the particles. So, that is the total porosity. So, this is defined as epsilon e, that is the interparticle porosity, plus 1 minus epsilon e. So, that is the solid fraction. Epsilon e is the interparticle porosity, 1 minus epsilon is the void fraction of the solid, right, and this should be multiplied by the epsilon p, right. So, this is the void fraction of the particles, and each particle will be having a porosity epsilon p. So, it will be multiplied by 1 minus epsilon into epsilon p. So, once you define this, bulk density can be defined. The bulk density is defined as rho bulk is equal to 1 minus epsilon e times rho p plus epsilon e times rho f. So, epsilon e is basically the interparticle porosity, where it will be occupied by the rho f, the fluid. Rho f is the density of the fluid. Okay. And rho p is density of the particle. So, epsilon is the void volume of the space, interparticle space. So, it should be occupied by the fluid, it should be multiplied by the density of the fluid. 1 minus epsilon e is basically the particle the void fraction that is occupied by the particle, it should be multiplied by the particle density. So, total bulk density is defined this way. It is basically an weighted average of the particle density and the fluid density, and the the weights are proportional to the void fraction. Okay. And rho p, the particle density, is defined as 1 minus epsilon p rho s plus epsilon p rho f. What is this? Rho s is the crystalline density. Crystalline density after crushing and compressing the solids. Solids without any pore. So, even in the particle, since the particle is porous, so it has two parts. One is the entirely solid part. What is there is no, that is the crystalline density. What is the crystalline density? You crush the particle, compress it, so that there is no pore, there exists no pore, and find out the density, that is the density of the absolutely solid particle. And some part of, since it is a porous in structure, the porous void fraction will be again occupied by the fluid. So, it will be multiplied by the rho f. So, again particle density will be an weighted average of the density of the fluid and density of the actual density of the solid, and the what are the weights? The weights will be proportional to the void fraction of each part, each system, that means the porous part and non porous part. Okay. Now, obviously, your crystalline density rho s is much higher than rho p and rho f, and your rho f, rho fluid, is much less than rho s and rho p. Okay. And also the pores are not of uniform size. We are talking about the pores within the solid particles. Pores in solid particles are not of uniform size. That means they are not straight cylindrical pores, even not cylindrical, they are not of, they may be tortuous, they may be of different dimensions. Okay. So, large molecules may be sterically excluded from the pores. Therefore, it is also possible, always possible, that large molecules cannot go inside the pores because their size is more. So, so it is called sterically excluded. So, size exclusion. Large molecules such as proteins, synthetic polymers may be sterically excluded some of the pores. They may not be sterically excluded from all pores, okay, because the pores are not of uniform size. They may be excluded from some of the pores which will be having the typical diameter which will be less than the diameter of these materials. So, let us define a fraction k d. This fraction is basically nothing but by the fraction of volume of pores that a molecule can penetrate. This fraction, let us call its k d. Okay. So, k d is the fraction of the volume fraction of the pores where a molecule can penetrate. Okay. So, the other pores it cannot penetrate. Okay. So, anyway, so we have basically defined some of the terms which will be useful to look into the solute movement into the column of a chromatography. Okay. So, by looking into the solute movement and by looking into the time required to cross the particular column length, you will be finding out that because of the difference in velocity. Why that velocity difference will occur? The velocity difference will occur because various solids will be adsorbed in different ways on the adsorbent. Okay. So, their velocity will be obviously different. Because of this velocity will be different, the residence time of these particular components through the column will be different. What does that mean? That means that stream that is going out of the column will be having a particular component reach at a particular time. After that it becomes dilute, and then after some time it becomes rich in another component. That means you are going to get peaks at different residence times. Okay. That means you are going to separate these solutes differently, and you can identify them easily and analyze them quite accurately. So, we will be looking into the theory of the solute movement theory in more detail, and of course, we will be taking up an example to compute these residence time of various solutes in a chromatographic column, okay, in the coming class. Thank you.